Just and to just switch on a light here. Nope, too bright. Okay, let's leave it like that. Okay. Like I said, good afternoon. My apologies. I have for the last hour or so tried to log onto this computer, which keeps throwing me out and disconnecting. Luckily, I had a new with Dr. James. We were able to connect a new, or he was able to connect a new computer. Okay. And I know this must be frustrating for you, and it is extremely frustrating for me, I can assure you. But I won't waste any more of your time. Start a new attempt. Just want to start a new attempt fresh. Reattempt. Okay. There we go. Now, like I said, my sincerest apologies. This is not how I wanted to start this session off. It is really not, but unfortunately I had no control over what happened. So, my name is Lucian, and I will be your tutor for today. Okay. And let me see if there are still people on Teams. Assume the people on Teams are listening or have logged off by now, stop listening. So, let's just see. If there's no one with questions, I'm just going to sit for a few minutes, wait until there's anyone has any questions. No one, any questions? Okay, so I'll just do some problems which might aid in your understanding of the work you've done so far. Now, you've recently started with electromagnetism, well, electricity and magnetism, the course on electricity and magnetism, electricity, magnetism, and optics. This course, FVV 102 and PHYV 102. Now, you will be dealing with all the concepts regarding electricity, magnetism, and basic optics. Now, you might not go in as deeply as you can go, but we will be teaching you the basics. Okay, now in this tutorial, I'm going to do a few problems that should aid you in your understanding of these concepts you've been introduced to for the last week. Now, question 1. This has to deal with charging, okay? Charging by conduction. Okay? During a physics lab, okay, so during a physics laboratory practice or during a physics lab session, a plastic strip was rubbed with cotton. So we have a plastic strip rubbed with cotton, okay, and became positively charged. So let's say we have a plastic strip, it is rubbed with cotton. Let's say this is the piece of plastic, we rub it with a piece of cotton, it's being rubbed by a piece of cotton, and it becomes positively charged. So after being rubbed, it becomes positively charged. This plastic strip becomes positively charged. The correct explanation for why the plastic strip becomes positively charged is, let's look at it. Okay, now we know that only electrons can be transferred. Okay, only electrons can be transferred. So in order for this plastic strip to become positive, it had to have gotten rid of its electrons. Okay, so its electrons the electrons for this plastic strip most likely went into the cotton. Okay, now let's look at the options they give us for answers. The plastic strip acquired extra protons from the cotton. That is incorrect. Protons, let's say A, we have B, C, and D. Okay, A is incorrect because protons do not move. They are tightly bound to the nucleus. Okay. Then we have option number 2, or option B, which states that, okay, sorry, I thought no one there was listening. Share. The guys on Teams, can you see now? Okay, thank you. That's Lifa. You can see we have Alizwa, Avene, Zola, and I am logged in as Dr. James. Okay, that is, although it is not me, I am Lucian, but this account refuses to go back to me. But guys, I really do apologize. After I just sent that email saying we will be starting at 2 o'clock, I got defeated by this computer and had to call in both the lab tech and Dr. James to come and help set things up because the computer kept kicking me out again. And I have been struggling, honestly, for the last hour trying to get into this computer just to set things up. Okay, so my apologies. But those of you who are currently listening, the question was, let me just repeat the question. We are rubbing a plastic strip. So this plastic strip here is being rubbed by a piece of cotton. Okay, and after being rubbed, the plastic strip is now positively charged. Okay, which one of those explanations can explain this phenomenon of now the plastic strip being positively charged? So we look at it. Option number 1, the plastic strip acquired extra protons. That option cannot be correct because protons are tightly bound to the nucleus. Okay. Option B, the plastic strip acquired extra protons during the charging. No, that is not correct. The protons, it could not have acquired protons because the only charges that move are the electrons. Option C, protons were created. No, we cannot create matter. It's the law of conservation of mass. Okay, matter cannot be created or destroyed, only changed form. Option D, the plastic strip lost electrons. That is the correct one. It has lost electrons to the cotton during the charging process. So option D, it cannot be B, it cannot be C. It is option D. Let's check if it's option D. And yes, it is indeed option D. Now, moving on. The next question. Okay. A student rubbed a glass object. Okay, so a student rubbed a glass object. There's an A, B, C, D options. Okay, so a student rubbed a glass object and felt together. So there is a piece of glass and a piece of felt. Felt is like a napkin, not a napkin, like a piece of material. Okay, and the glass becomes positively charged after being rubbed together. The glass becomes positively charged. Which of the following statements is or are true? Circle all that apply. Okay, so we know for a fact the only thing that could have happened is, or well, one of the things that could have happened is that the glass lost electrons. The glass donated electrons to the piece of felt, which has now some electrons in it. Okay, so now we need to pick which one of those options are correct. Select one or more. So one or more could be correct. Okay, the glass gained protons during the rubbing process. That is incorrect. Okay, protons cannot move. They are tightly bound to the nucleus. The protons cannot move. They are tightly bound to the nucleus. The next option is, let's move there. The felt became charged negatively during this rubbing process. That is true. The felt can become negatively charged. The felt can become negatively charged due to the migration of electrons from the protons from the glass to the felt. Number C, or letter C, charge is created during the rubbing process. No, the law of conservation of charge says charge cannot be created or destroyed. So it cannot be C. D, if the glass acquired a charge of plus 5 units, then the felt acquires a charge of negative 5 units. D can be correct. It can indeed be correct. And E, actually there's an option E also. So E says once charged in this manner, the glass object and the felt cloth should attract each other. Yes, if they are charged like this, they should attract each other. So let's see. We have B, we have D, and E as correct. They can all be correct options. Let's look. B is correct, D is correct, and E is correct. And the correct answers are: the felt became charged negatively during the rubbing process. If the glass acquired a charge of positive 5 units, then the felt acquires a charge of negative 5. And once charged in this manner, the glass and object could attract each other. Excuse me. So, that, ladies and gentlemen, is question number 2. Are there any questions? Look, I am here to answer your questions if you have them. If not, then I continue doing a few problems. But if you have questions, please let me know right now. The guys that are currently on Teams, can you let me know if you have questions? If you have questions, please let me know. Anyone? Let me see the chat. Okay, thank you, Zola. You answered there in the chat. Thank you. Okay, question number 3. Metal spheres A has 4 units of negative charge. So let's see. Metal sphere A. Let's draw it. A. Metal sphere A has 4 units of negative charge. So 1, 2, 3, 4. If you have any questions, it doesn't have to be about this particular work. It can be any of the work you've done so far in physics. Okay, if you have any questions, regarding the work you've done so far in physics, please ask me. If you have any questions about what you've done so far, you can ask me. If not, I'm going through some problems that might aid you later on, either in a test or an exam or in your tutorials or practicals. So a metal sphere A has 4 units of negative charge, and metal sphere B has 2 positive units of charge. So 2 positive units of charge. The 2 spheres are brought into contact. So they are brought into contact. That's 2 positives, 4 negatives. What is the final charge of each state of the sphere? And explain. Okay, so the final charge, when they are moved apart, what is their charges again? Okay. Now, when they are in contact, since they are metal, these charges will flow across. Okay. 2 of these charges will immediately flow across, leaving one of the spheres neutral and the other one with a charge of positive 2. But charges tend to distribute equally. Okay, so after this happens, 2 of them will flow over, leaving 2 positive over, and they must touch, they are in contact. 2 of them will flow over, leaving 2 negative charges on this side and a 0 charge on that side. But charges always tend to distribute equally or evenly, meaning one more will go to this side so they can have an equal charge. So what we'll be left with in the end is the following. After they've made contact, we'll have A with 1 charge and B with 1 negative charge as well. And you can actually work it out. When you bring them into contact, you have 4 negative charges plus 2 positive charges. You bring them into contact, then you split them. This gives you an answer of -1. So each one has a charge of -1. The guys that are on teams, does that make sense? Does it make sense? On teams, can you just... Okay, Zola and Lifa and Alizwa. It seems it makes sense. Thank you guys. Thank you guys. Don't worry, I will not be keeping you long. Okay, so it is not a long tutorial. We tend to, our primary focus is to answer questions. That's why we come with some problems in case you don't have any questions, so that we do some basic problems that might aid you in your studies. Okay, so the answer we've seen is -1. Let's look at this one. A says -1 because -4 plus 2 is equal to -2, and then the remaining -2 charges distribute on both spheres so that each sphere will have a -1 charge. So A is correct. It's not -2, it's not -3, and it's not -4. The answer is A. Let's check it. Just remember that question. All you had to know is, so A is correct, yes. All you had to know is that when 2 metal spheres are brought into contact, the electrons will distribute themselves evenly between them. But first, they will make one of them, if one of them has positive and one negative, then they will first cancel out the positive, and then they will divide the remaining negative charges between them. Like the question says, the remaining negative charges, after they've been equalized, all the positive has been made redundant, the remaining negative charges are distributed evenly or equally. Okay, now question number 4. Let's see on question number 4. 2 neutral conducting spheres are in contact with each other. So we have 2 spheres, they are in contact with each other and they are neutral, meaning they have no net charge. But they are insulated from the rest of the world. So insulated. It's just these two spheres, sphere A and sphere B, two neutral spheres, meaning they have no net charge. Now, a positively charged rod is brought near the right sphere. Okay, so a positively charged rod. So here we bring a rod with a positive charge. Okay. It comes close to the, brought near the right sphere. It doesn't touch, see? It doesn't touch. Now, the positive rod is removed and then the spheres are separated. The result is, now, when we bring a positive rod close to it, okay, it will attract all the negative charges. Remember, although it is neutral, it has both positive and negative charges. Okay? It has both positive and negative charges. It will attract all the negative charges from both sides of these spheres. Let me make an example. Let's say both of these spheres have one positive, one negative, one positive, one negative, one positive, negative, positive, negative. So each one has two positive and two negative charges. Now when I bring this positive rod close to it, it will attract all, since it is metal spheres, it is conducting. So when I bring this rod close to it, it will attract all the negative spheres. Now you know that in conductors, electrons are free to flow. So this is going to happen. Okay, this is going to happen. All the electrons are being moved, because basically now it's just one conductor because they are in contact. The electrons are moved from the right sphere. All of them, all four of the electrons are now in one sphere, plus its two positives, and plus this one also just contains its positives. Okay, the positive, when this is what happens when the positive rod is now removed. The rod is removed. Rod removed. Removed. This is when the rod is removed. We have negative charges sucked or attracted to the right hand side where the rod was. The result is the left sphere is, let's see, the left sphere is now positive and the right sphere is now negative, because these two will cancel each out, which means the left sphere is more slightly negative and the right sphere is positive, slightly positive. The left sphere is positive and the right sphere is negative B. That's question number 4. So B can be an answer. The left sphere is neutral. No, cannot be neutral. The left sphere is negative and the right sphere is neutral. That cannot be. They must both have charge, and both spheres are neutral. They can both still be neutral. The thing is, when you remove, you see, this is what happens after you've removed the rod. When they are still in contact, remember, they are not moved apart. Okay, so this is why I only stop there. Okay, now they are still in contact. When the rod is removed, everyone goes back to how it was. When the rod is removed, this is when the rod is there. Okay, it's attracting. But now when the rod is removed, everyone goes back to how it was before the rod was there. So everyone goes back to how it was before the rod was there. Okay, so the reason why I stopped there is because I wanted to show you this particular answer here. You say here, they are in contact with each other. Okay? They are not moved apart. If they were moved apart, with the rod still there, one of them would have been left negative and one of them positive. But now, each one has a net charge of 0. So, let's look at the answer. Both spheres are neutral. They have a net charge of 0. there is no grounding wire. That's what we call grounding wire. They have not been separated, and there's no grounding wire that leads the charge away. Any questions? If you have any questions, please ask now. Any questions, guys? Do you guys understand why they are still both neutral at the end? Because even though a net charge was induced, when the rod was removed, that positive rod was removed, the charges were distributed themselves as to how they were originally. Okay, is everyone good with that? Okay, Alizwa, you seem to be snapping that. Also, Lifa and Avene. Okay, Zola, you have a question. You can ask. If you have a mic, you can ask. If you not, you can just type the question. Or did you indicate that you understood? If you have a question, you can ask. But if you feel free to stop me anytime. Okay, Zola. I assume you were just saying that you got it. Okay, so let's now get to the meat questions. And this is a question I did with my MFS group earlier on. Okay. It's a question that most people tend to struggle with. Okay. Luko, if you have a question, just ask. Go ahead.
Uh,
Okay.
okay. Can you please repeat the last part? Where you said that the electrons moved and then the one at the right side gained some electrons. So I want to understand that. Can you please clarify that?
Okay. Cool. No problem. No problem. Okay. So this why they are still neutral at the end. Okay. Remember, they are in contact the whole time. They are not moved away from each other. Okay. We bring in a rod that is positively charged. Okay. This rod attracts all the negative ones because they are free to move. They are in contact, so the electrons can move. The positive charges just stay exactly where they are. They cannot move. So it attracts all the negative charges. But then we remove the rod. We remove the rod. Now remember, in our previous question, we were asked what happens when those spheres were brought into contact, what will be the final charge? Okay, now remember I said the electrons will immediately get rid of all positive charge. Okay, so two of them will flow back. Two of them will immediately flow to that side to get rid of this excess positive charge. Okay, two of them will be attracted to those two positives, and they will be making this one negative, or not negative, neutral. Okay, and what is left on the side? One, two positives and the two negatives that are still left. Okay, now I told you the electrons will tend to first neutralize any positive charges. They will first tend to neutralize positive charges, and after they've neutralized the positive charges, what they will then do is distribute equally those that are still left. But are there any electrons I remember, I should have said the excess electrons or electrons that are still too much, they will then distribute it equally amongst the charges that are in contact. Sorry, they should be in contact here. These two should be in contact. Okay. Now, since there is no excess charge, there is no net negative charge. Okay, the net negative charge in this case, because we've already taken two electrons away. Now the net negative charge is zero. Okay, zero electrons. There is zero extra charge, zero extra negative charge. Okay, and how do we distribute zero equally? We divide it by 2. 0 by 2 is still 0. So no electrons are being distributed further. Okay, meaning we are still left with one has zero net charge and one is zero net charge, meaning they are both neutral. Does that make sense? More or less? Okay, thank you. Number 5. This one is one that is important for many reasons because I struggled a lot with this concept. Let's say object A, it has 2 nanocoulomb. Object A has 2 nanocoulomb charge. Okay, and object B has 6 nanocoulomb charge. What can we say about the forces between these two objects? Okay, this is what you should take as a fact. There was once a guy by the name of Isaac Newton that said if one object exerts a force on another, then that object exerts the exact same force on that one, except it will be in the opposite direction. So it doesn't matter what size of the charge it is. It doesn't matter if this one is 100 times bigger than this one or whatever. If this one exerts a force on that one, it exerts the exact same force one, but only in the opposite direction. Okay, so you can calculate the force between these two. Okay, it will exert the exact same force one on the 6 nanocoulomb as the 6 nanocoulomb exerts on the 2 nanocoulomb. So the force, we call it object A, the force that A has on B is exactly the same that force that B has on A, but the only difference is the force that B has on A is in the opposite direction. Does that make sense? By a show of hands, you guys in teams, does it make sense? It's Newton's law. Force is always the same, just different. Okay, thank you. It's just different. So the forces, it doesn't matter. This one can be 100,000 times bigger, this charge. It doesn't matter how big it is and how small this one is. The force between them will always be the same. It will just be in opposite directions. So let's see here. It will be B then. B will be the answer. Force of A has on B will be exactly the same as B on A, only in the opposite direction. Their forces will always be exactly the same. And there you have it. B is the correct answer. Question 6, and I think we're almost done now. Question 6. Two small non-conducting spheres. So two small non-conducting spheres, okay, is charged positively. So we have two small spheres charged positively, and they have a combined charge of 40 microcoulomb. So the charge of one sphere plus the charge of another one is equal to 40 times 10 to the negative 6 coulomb. Oh, go back. Negative 6 coulomb. Okay. Now, if we work it out, well, we can rearrange this to say that Q1 is equal to 40 microcoulomb minus Q2. And let's call this equation 1. Okay. We can see from this it's going to be a simultaneous equation. Now Q1 is equal to 40 microcoulombs minus the charge of Q, because they must both be equal to 40 microcoulombs. Okay. Then they go further. They say when the two spheres are 50 centimeters apart, each sphere is repelled from the other by a force of magnitude 2 newtons. So if they are repelled by each other, it means they have the exact same charge. Okay. And they have a charge of 40 microcoulombs, meaning they are both positive. They are both positive charges. So we know now that they are both positive charges, and when they are 50 centimeters apart, they have a force of 2 newtons. So 2 newtons when they are 50 centimeters apart, which is just 0.5 meters. 0.5 meters. We have Coulomb's constant, which is 9 times 10 to the 9. And then we have charge 1, which is Q1, and then we have Q2. Okay, and this, ladies and gentlemen, is equation number 2. So we have equation 1 where Q1 is equal to 40 times 10 to the negative 6 minus Q2. So we can just substitute that into Q1 and into equation 2, and then we can work out what Q2 is. Let's do that. So the answer should give you 2 newtons, and it is 9 times 10 to the 9. Excuse me. And it is Q1. We have said that Q1 is equal to 40 times 10 to the negative 6 minus Q2. This is Q1. And then you multiply it by Q2. And this force is obtained when they are 0.5 meters apart from each other. Now we can actually solve for Q2. Okay, we can solve for Q2. Right? You can multiply on both sides and then subtract. But anyway, you can multiply on both sides. Multiply that in. I will not insult you by doing the whole thing, but maybe I should. Okay, so let me do a part of it at least. What's left on this side is 9 times 10 to the 9. And we are left with 40 times 10 to the negative 6 minus, or Q2 at least. We're multiplying Q2 in, multiplying it in, minus Q2 squared. Don't get them confused. This is a subscript and that is the squared for the superscript. And then on this side, 0.5 squared multiplied by 2 gives you 0.5 squared multiplied by 2 gives you 0.5, because 0.5 squared is 0.25 and multiplied by 2 is 0.5. This is the equation. This is the equation. Now if you multiply on both, if you divide on both sides by 9 times 10 to the 9, you get 5 times 5, 5.5 times 10 to the negative 11. On this side, if you multiply on both sides by 9 times 10 to the 9, and on this side you're left with 40 times 10 to the negative 6 Q2 minus Q2 squared. Okay? And in this case you can obviously go further and simplify, but using your formula, algebraic formula, to solve for that quadratic equation, we get that Q is equal to 1.4 times 10 to the negative 6 coulomb. That is Q1. No, sorry, Q2. That is Q2. And you can of course then get Q1 by subtracting it from Q2. Okay, so determine the magnitude of the smaller of the two charges. Okay, so if this is 1 and the combined is 40, combined they should be 40. This one is indeed the smaller charge. Q2 is the smaller charge, so it is 1.4 microcoulomb. Let's check. 1.4 microcoulomb. And yes, it is indeed correct. Did everyone understand this one, the math at least? Okay, it is just a simultaneous equation. You just have to solve Q1 and Q2. You guys in teams, did you understand? Okay, most of you seem to have gotten it. Okay, the last two is, if you need me to explain again, you just need to tell me. The last two questions are multiple choice and then we are done. Okay, it says the diagrams, question 7. Let me erase this. Question 7 says the diagrams below show two uniformly charged spheres. The charge on the right sphere is 3 times as large as the charge on the left sphere. So the charge on the right sphere is 3 times as big as the charge on the left sphere. Which force diagram best represents the magnitudes and directions of the electric forces on the two spheres? Now, all of them are positive, so they should be pointing in opposite directions because they are repelling each other. Okay, so let's see. We have 2 positive here, and then on this side, we have 6 positives. 6 positives. First of all, they are both pointing in opposite directions, and like we said early on, the force will be the same on both sides. In this case, they are both positive, so we'll be pushing each other away with the exact same force, just in opposite directions. Okay, this force is going that way, and that one is just the force, same force, but in the opposite direction. So the only one that comes close to describing this scenario is number 4. Okay, it's the only one where the arrows look remotely equal to each other. So 4, select one, number 4, D. So D is the correct answer. Answer is D. And let's see if it's correct. Yes, it is D. Last question for today. This is just a brush up of everything you have done so far on Coulomb's law and stuff. Tomorrow you will go into the meat of the problems of doing actually Coulomb problems. Okay, if you have questions tomorrow, just go ask. I think Arnold will be tutoring tomorrow. The day after that, James. Then next week Tuesday, me again. If you have questions, please ask. Wait until 2 o'clock on a Tuesday. Then you have a free session. Okay, we do these questions just to help and aid you, but our primary goal is to answer your questions, any questions you might have regarding physics. So that is 2 hours for 6 hours per week of free physics tutoring if you are available. Now, question number 8. A negatively charged particle with a charge of negative microcoulomb is placed at the center of a uniformly charged cube. Okay, so a cube, we have a cube, a uniformly charged cube. That is a terrible cube, by the way. We have a cube, and right at its center is a charge of negative microcoulomb placed at the center. Okay, and it has a side of 1 millimeter and a total charge of 3 coulomb. Now this 3 coulomb is spread out all over these faces, meaning this face here on top has the exact same charge as this one, which has the exact same charge as this one, which is the exact same charge as the bottom one, which has the exact same charge as the back one. Okay, now what is the total force acting on the particle in the center? Okay, find the magnitude and the direction. Now here's the wonderful thing about this particular problem. If every face has the exact same charge, that means the charge on the top will either push or pull with the exact same magnitude as the charge on the bottom because they are the same magnitude. Okay, it's kind of like this. Let me draw it in a different way. Let's say this is the charge in the center. I have a positive up here and a positive the same distance here. Okay, let's say this charge in the middle is also positive. It will push it up and that one will push it up. This one positive will push it to the left and this one will push it to the right. Okay, now on every face at the back there is also one. It will push it to the front, and the one at the front will push it to the back with the exact same force, meaning all of these forces will eventually cancel each other out because they are all exactly the same. Okay, they're all exactly the same, so they will all cancel each other out, meaning the net force of the particle at the center will always be 0. Let's see, E0. Let's see if it's correct. Yes, the net force is 0. Okay, this is for question number 8. So the force on the bottom one is 0. Ladies and gentlemen, okay, you guys Thank you for listening. If you have any questions, maybe you want to speak to me, just ask. Thank you, Alizwa. That is that is very kind of you, and I do apologize again for starting late. Now it seems to be set up tomorrow. For tomorrow as well, I will not be switching it off. So you guys, do me a favor. If you ever struggle with your physics, okay, if you struggle with physics, you understand, even if it's a small concept, every Tuesday, every Wednesday, every Thursday, okay, I know you, some of you have practicals, but if you struggle with even one single thing, from experience I can tell you that this module is difficult. It is slightly more difficult than the first semester one. So if you struggle with anything, please, 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 please send me an email. I will send out an email saying, if you struggle with anything in physics, send me an email. I will answer it and get back to you. Even if I have to set up a Teams meeting between me and you so that we can get to the bottom of this. But if you, for every Tuesday, every Thursday, every Tuesday, Wednesday, and Thursday, if you have a physics question, remember, we do these problems if there are no questions being asked. So please ask questions as much as you can. You have, for 2 hours, you have a free tutor that you don't have to pay for 2 hours. So please come ask us questions. We will try to explain it to you as best as we can. Even better, if you have questions, those of you that are currently listening, if you have questions, please email them to me beforehand so I can actually work it out, find the easiest way to explain it to you. Okay. Those of you who don't know me, my name is Lucian Pullen. I have 2 email addresses. Okay. Try to use the one. If you do send me an email asking for help in physics, use the email 215323, the one that has my student number in, not my name. The one that has my name in is my staff account, and that one I check it every day, but the other one is the one that is usually gives me my pop-ups. Okay. Thank you guys. Thank you for listening. If you want to, you can join tomorrow with Arnold if you have questions, or on Thursday with James, or next week with me again. Okay, thanks guys. See you. Bye bye.